Today we're going to talk about castable urethane basics. This will move us into the industry trends, and then we'll discuss adhesive fundamentals. We'll move on to test conditions and failure modes, and then Christina will take over with data and observations and trends. So first we have to talk about what castable urethanes are. It's a two-part urethane system, with the side A being a liquid urethane prepolymer with a known percentage of isocyanate. Side B is either a hydroxyl or an amine type curative. They can have any or none of the following additives: plasticizers, fillers, degassing agents, colorants, and etc. Now we're going to talk about some variables that can affect castable urethane performance. You can have aromatic versus aliphatic isocyanate. Let's say you wanted to produce a good that had a clear elastomer. Well, then you'd have to choose the aliphatic. Most of the industry uses aromatic. They're cheaper and they work well. Polyester versus polyether polyol. Let's say you wanted to produce a good that worked well in high moisture or water areas. Then you'd want to choose a polyether because the polyester will hydrolyze. So stoichiometry can also affect how the castable urethane performs. A stoichiometry is the ratio of the curative to the isocyanate. It's often referred to as the index number. The index number can run from 85 to 130. However, typical for the industry is 90 to 105. For our testing, we ran 95. This means that there's 5% leftover isocyanate to bond to. Now, polyol chain length can also come into play. Let's say that you wanted to produce an elastomer that was quite flexible. Then you'd have to choose a long chain polyol. Multifunctional crosslinkers and additives can also affect castable urethane performance. So why use castable urethanes? Well, they're pretty easy to use and process. Basically, you mix, pour, and cure. There's a pretty low barrier of entry into the market. Most people could set these up in their garage. They have great performance properties: abrasion resistance, oil resistance, tear and cut resistance, but above all, high load bearing capabilities. There's no other elastomer on the market that can match these, and it's why they're used in wheels, rollers, bumpers, and mining and oil field equipment. Now, they do have some disadvantages. They don't perform particularly well in wet, hot environments, and in continuous high temperature service at 121 degrees C and above, they tend to degrade. They also tend to swell in ketone solvents, and they're pretty expensive.
Okay, at this point in time, we're going to introduce our first poll question, and that first poll question is, what sector do you supply products to?
Now we're going to move on and start talking about the industry trends here, and you're going to find some of these last things a little ironic. So the current industry trends are towards higher heat applications at 93 C and above, and higher humidity and higher temperatures, coupled with direct water exposure with heat. So why is this? There are two specific reasons. One is urethane manufacturers are starting to make better elastomers that can withstand these conditions. And the second part is engineers are taking advantage of these high load bearing capabilities of polyurethane, and they're creating complex parts that might undergo vibration, flexing, or impact, and they can generate an internal temperature increase. If that heat is not dissipated correctly, the urethane can fail or the bond can fail. So this is the central problem. Many castable urethane adhesives were not designed to perform at elevated temperatures or in hot, wet conditions. You simply don't develop an adhesive to meet the disadvantages of an elastomer. But since then, manufacturers are making better elastomers, and now it's time for the adhesives to catch up. And so that's why we're developing these new adhesives, Chemlok 701 and 701-702. Now let's talk about adhesive fundamentals. So taking a look at the schematic here, imagine that this is an industrial part or a wheel, and the bottom part of this in gray is either the metal or the plastic substrate. In yellow is the adhesive that's applied on top of this. Green is the diffusion zone between the adhesive and the urethane, and blue is the body of the urethane. Taking a look in the upper right-hand corner, you can see what we use, some of the tools we use to develop new products. So one of the first things is mechanical adhesion. If you take a look in the lower right-hand corner, you can see a depiction of mechanical adhesion. How do we get this? We look for the part to be abraded or grit blasted, and we want to bond to those imperfections in that surface. And that's how we get our first bite of mechanical adhesion. It increases the surface area and the surface energy. And then during the cure process, we can get chemisorption, adsorption, and or hydrogen bonding at that interface. While this cure is going on, we can cross-link the adhesive system and diffuse from the adhesive up into the urethane and from the urethane into the adhesive. The chains entangle, you can get hydrogen bonding, and this is how you get your first covalent bonding and get that first bite into the urethane and get that rubber retention. So while all this is going on in the body of the urethane during the cure process, you start to get covalent bonding. And then in the post-cure, what you have is a alignment of the hard blocks in the polyurethane, and you get hydrogen bonding, and it rounds out your properties. So when we're developing an adhesive like this, what we like to think of is each one of the interfaces that we encounter is like a link in a chain. And we know that chains fail at their weakest link. So it's incumbent upon the developer to develop an adhesive that bonds to the metal substrate and up into the urethane in such a fashion that when the urethane or the part is destructively tested, it fails at the weakest link, which would be in the urethane, and you end up with rubber retention. So those are some of the basics on adhesive fundamentals and adhesion and how we go about developing new products. Now let's talk about some benefits and properties of the new adhesives. They bond a variety of castable urethanes. 1 and 2K systems are available. They're stable out to a year, no free isocyanate in the 1K. Pretty easy to apply, you can spray with no dilution or brush. These were developed not to need a pre-bake. However, should your system need one, both the 1K and the 2K can accommodate. Chemlok 701, the 1K, has solids of 21 to 23% and a viscosity range of 2 to 300 CPS. It's blue and has a cure temperature range of 100 to 150. Chemlok 701, 702 has a solids content of 28 to 31%, 250 to 350 CPS for viscosity. It's blue and also works in that same cure temperature range. For this particular ratio, we use 10 to 1. You will have a pot life of anywhere between 1 and 3 hours. Now, later on in the presentation, Christina is going to refine this ratio and talk about some of the trends with it. Now let's talk about test parts and conditions. We use the ASTM International D429 method B. You can see a schematic beneath here. For the coupon preparation, we grit blasted the steel with 24 grit aluminum oxide, MEK rinsed, and we were looking for an anchor profile of 25 to 75 microns. You can see a picture of a micrograph at the right, a depiction of what this surface might look like. You can see higher surface area and higher surface energy. This will certainly help the adhesive wet out onto this surface and give us that first bite of mechanical adhesion.
And now for our second poll question, what substrates do you bond castable urethanes to?
Now a bit about test conditions and application. These were spray applied using an HVLP gun with a dry film thickness range of 25 microns, what we were shooting for. However, it does work between 20 and 30 microns. And later on, Christina will talk about a refinement of the DFT and how that affects the performance. These were dried at 93 degrees C for 30 minutes, no additives, just the A side and a curative. Open mold, cure plus post-cure. Taking a look at the pictures underneath here in the hand cast process, you can see the first 3 pictures are all you need to start your own casting operation. You need the proper PPE, you need an oven, and a mold. Underneath you can see a technician adding the B side curative to the A side, stirring it so as to not entrain air, and then adding this and pouring it over the parts into the mold. A half an hour later, you ended up with a molded plaque. Now, this plaque has to undergo a post-cure in order to develop full properties. After that, we did environmental tests. Primary adhesion on the tensile tester, 45-degree angle at 305 millimeters per minute. On the far left, you can see an ASTM part. In the center, you see the tensile tester. And on the right, you see a destructively tested part with rubber retention. For boiling water, we used 100 degrees C water, unstressed for 8 hours, tested at RT on the tensile tester if they pass. In addition, we did hot tear testing on a hot box at 121 degrees C. You can see a technician in the picture on the left. Adding the parts to the box, they get a 2-hour soak. After the 2-hour soak, they are tested hot in the box. Now a bit about our castable urethane grades. So we looked at quite a few different grades of polyurethane when we were developing these products, but for this particular testing, we talked to the manufacturers of castable urethanes and asked them what their highest volume products were, what is the most mainstream products that are used on the most goods, and this is what they came back with. And you can see that there's 4 different here. They're all TDI based, they're all cured with mocha. 2 are polyethers, 2 are polyesters, 2 are Shore A85s, and 2 are Shore A95s. For the cure, it's all 100 degrees C, ranging from 20 minutes to 40 minutes, and for the post-cure, it's 100 degrees C for 16 hours. Now, it's very important that the post-cure is included, because if you don't do the post-cure, you won't get your final performance parameters for your parts. Now we need to talk about failure modes per the ASTM International D429. In the next couple of slides, Christina's going to talk about data and the trends, and it's important that we're all on the same page about failure modes. R, or rubber retention, is the most important. What does that mean? It means that the adhesive has bonded at the interface to the metal substrate and with the polyurethane in such a fashion that when it's destructively tested, the adhesive bond is actually stronger than the polyurethane, and it fails within the polyurethane, giving us rubber retention. RC, rubber to cement. This is a failure at the interface between the adhesive and the polyurethane. Some of the reasons: thickness, contaminated surface, or pre-bake cycle. The next, cohesive. This is a failure within the adhesive, and this is almost always a thickness problem. CM, cement to metal. And this is a failure at the interface between the adhesive and the metal substrate. Why? Poor anchor profile, blast residue, contamination, and or oxidation. It's important to note that your surface of your metal has to be clean and properly abraded so that you get that first bite of mechanical adhesion so that you can get that bonded good. And now I'll turn it over to Christina, who's going to talk about the data and some of the trends and observations with that.
Thanks, Brian. After the success that we saw in Chemlok internal benchmarking tests, as well as our customer trials, we decided to conduct a robustness study for the product. Our testing was focused on determining the optimal application ranges for variables like the Chemlok 702 curative ratio and dry film thickness. Our goal was to establish working ranges for these variables to ensure the optimal performance of 701. This first series of charts are presented to show the effect of Chemlok 702 ratio on the bond performance for primary adhesion testing. We'll look at charts both with and without a pre-bake for each of the 3 dry film thicknesses tested. These first 2 charts represent a fixed dry film thickness of 0.5 mil, or about 13 microns. The top chart is the data with a pre-bake, and the bottom chart is the data without a pre-bake. We see similar trends with and without pre-bake at 0.5 mil. As the 702 ratio increases, bond performance generally decreases. The lowest bond strength and the highest percentages of cement to metal failure, represented by the orange bars, occur at a 5% by weight ratio and higher. This data set shows that the highest Chemlok 701 performance occurs at a 0 to 2.5% ratio of 702. Now at a 1 mil or 25 micron fixed dry film thickness, the trends look similar for the data. As the 702 ratio increases, we see the highest failure rates at 5% Chemlok 702 or higher. And once again, the best bond performance is at 2.5% or lower. Compared to the half mil condition for film thickness, we can see that at 1 mil, there's lower rubber retention with the pre-bake condition and higher rubber retention without pre-bake. The increase that we see in rubber retention with film thickness is on the higher durometer compounds, the A995 and the A9-5. The bond strength with pre-bake hovers around 200 pounds per square inch, and without a pre-bake is around 250. As seen with the other dry film thicknesses, there are similar trends in the data with and without pre-bake at the 2.5 mil dry film thickness condition. The bond performance is the best at lower curative ratios, and we can observe bond strengths at both pre-bake conditions in excess of 300 pounds per square inch. The rubber retention is higher without a pre-bake, and the greater percentage of failure occurs with a pre-bake of 2.5 mils than 1 mil. Now we have another poll question, and that question is, how do you apply adhesive to the substrate? This next series of graphs convey the differences in bond performance based on dry film thickness for both boiling water and hot tear environmental testing. We did 8 hours of unstressed exposure in boiling water, and our hot tear pull testing was run at 250 degrees Fahrenheit or 121 degrees Celsius. The left chart represents pre-bake, and the right represents no pre-bake. These two charts are showing the boiling water results for Chemlok 701 without any Chemlok 702 added. All of the compounds tested resulted in 100% rubber tearing bonds at these conditions. You can see this by the blue bars. With pre-bake, across all 4 elastomers, the lowest bond strength is observed at 0.5 mil. Without pre-bake, we see somewhat of a trend that at higher film thickness, we see higher performance. The A9-5 is the outlier to this trend. And at both pre-bake conditions, the A9-5 has significantly higher bond strength at 1 mil film thickness than 2.5 mils. These charts represent the same curative condition, 0% Chemlok 702, for the boiling water test. Now this testing, as Brian mentioned earlier, was conducted for 8 hours and the samples were unstressed in the boiling water. We can observe 100% rubber retention with pre-bake and mainly rubber retention above the 0.5 mil condition without pre-bake. With pre-bake, there's a decrease in bond strength observed at 2.5 mils. Without pre-bake, bond strength varies across film thicknesses, and we really can't distinguish a clear trend from this data set. Now let's move on to results for hot tear testing. At a 0% ratio of 702, we can see 100% rubber retention across the board for the pre-bake results, and almost all rubber retention for the no pre-bake condition. Both with and without pre-bake, the highest bond strength is observed with the A9-5 elastomer, the higher durometer polyester-based urethane. There isn't really a significant variation in performance based on dry film thickness with the pre-bake condition, but without it we can see that the lowest bond strength is generally at 2.5 mils. The highest thick rubber retention is seen on the softer compounds across all pre-bake conditions. Now we're viewing boiling water results at the 2.5% curative ratio. With a pre-bake, the lower durometer A85 elastomer yielded a higher rubber retention than A95. In contrast, we can see that there's a higher bond strength with the A95 than the A85. This pattern is common given that there's a difference in the durometers. Without pre-bake, we once again can see that the A85 has better rubber retention than A95. The highest bond strength, exceeding 250 pounds per square inch, occurs at the 2.5 mil condition on the A95 compound. Now we're viewing hot tear results for 2.5% ratio of Chemlok 702. The highest thick rubber retention is seen on the softer compounds, the A85 and A8-5 for both pre-bake conditions. There are a few data points missing for the A85 elastomer. This compound tore during the hot tear testing prior to tensile testing, and it wasn't able to be evaluated for the missing conditions. The A85 was noticeably weaker than the other elastomers when exposed to high heat. We can see that rubber retention is higher without pre-bake. With pre-bake, we start to see RC failure, unlike the data without the curative. Now that we've added 2.5% 702, the preheat is allowed for cross-linking to occur within the adhesive prior to the casting process. And that's why the failure is occurring at the rubber interface with the pre-bake. There's also some cement to metal failure with the stiffer compounds for the non-pre-bake data. For both pre-bake conditions, the average bond strength is generally higher for the stiffer compounds. The highest bond strengths, greater than 200 pounds per square inch, are observed with the A9-5 polyester-based urethane. And generally speaking, the half mil dry film thickness condition yielded the highest bond strength for this data set. Here's the data set for 5% 702 ratio in the boiling water test. For the pre-bake data set, the softer compound yielded higher rubber retention. Bond strength is consistent across compounds and dry film thicknesses in the range of about 100 to 125 pounds per square inch. For the no pre-bake condition, we also see higher rubber retention with A85 than A95. Similar to the primary adhesion no pre-bake results, the lowest bond performance for boiling water without a pre-bake occurs at 0.5 mil for both elastomers. You can see the drop-off in bond strength on the graph to the right. Now reviewing hot tear results at 5% Chemlok 702 ratio. Generally, the rubber retention is higher for the lower durometer compounds under both pre-bake conditions. We see mostly rubber retention with no pre-bake, and the ratios of rubber tear are higher without pre-bake than with pre-bake, as we saw with the 2.5% ratio. The quantity of rubber to cement failure is even higher with pre-bake for 5% than 2.5%. The curative will react within the adhesive at room temperature, so when additional heat is introduced, it will react even faster. The cross-linking that occurs prior to molding results in fewer reactive sites for adhesion to the urethane, so that's why we're seeing failure at the rubber interface. Now moving on to bond strength, we can see that both with and without pre-bake, the highest bond strength is observed on the A9-5. There isn't a significant trend in dry film thickness with either pre-bake condition, and there's little variation based on dry film thickness for the graph of results with pre-bake. Here are the results for boiling water testing at a 7.5% ratio. The trends in the data are similar for both the pre-bake conditions, and for both conditions we see a higher rubber retention with A85 than A95. Overall, the best performance under these conditions is at 2.5 mils. Here are the results for hot tear testing at a 7.5% ratio of Chemlok 702. Generally, rubber retention is once again higher for the lower durometer compounds under both pre-bake conditions. We see mostly rubber retention without pre-bake, and overall the no pre-bake condition yielded higher rubber tear than the pre-bake condition. Similar to the data set for 5%, there's higher rubber to cement failure with the preheat due to that cross-linking of the Chemlok 702. We're seeing a trend in the data that the higher ratios of 702 call for lower or ideally absent preheat to maximize rubber tearing bonds. Now moving on to bond strength, we see that both with and without pre-bake, our highest strength is once again observed on the A9-5 elastomer. For the softer elastomers, at both pre-bake conditions, we don't really see any dry film thickness trend in the data. However, for the higher durometer urethanes, there is a trend. As dry film thickness increases, bond strength increases for these compounds. These results are for boiling water testing at 10% Chemlok 702. These results look similar to those for the 7.5% curative ratio. For both pre-bake conditions, there's higher rubber retention on the A85 than the A95, and overall we see that the highest average bond strength occurs at 2.5 mils dry film thickness. Here are the results for hot tear testing. As we observed in most of the other curative ratios, the rubber retention is higher in hot tear for the lower durometer compounds. This is true under both of the pre-bake conditions. And we see that rubber retention drops off for the stiffer compounds. Now that we've looked at hot tear results across all 5 of our curative ratios, we see that the trend is that higher rubber tear is yielded without a pre-bake than with a pre-bake. And in terms of bond strength, that trend is opposite for this data set. Both with and without a pre-bake, the highest bond strength is observed with A9-5, specifically at 2.5 mils dry film thickness. As the DFT increases, the bond strength of the stiffer elastomers increases. We can observe this with both pre-bake conditions, and it follows the trend that we saw with the 7.5% curative ratio. Now that I've covered the data for the environmental tests, there are some trends and observations that I'd like to highlight. The table on this slide summarizes the trends in bond performance based on the ratio of Chemlok 702 and the dry film thickness. Dry film thickness showed consistency in performance within our tested range. However, the curative ratios showed a narrower window of performance at the lower levels. So overall, a Chemlok 702 ratio of 0 to 2.5% and about a 1 to 2 mil dry film thickness range are the ideal conditions for bonding. The table on the slide summarizes the curative ratio and dry film thickness trends in the data. The table shows that a higher curative ratio is correlated to a lower performance under all of the pre-bake conditions. Generally, lower 702 ratios are preferred, but if a higher ratio is used, a dry film thickness of 1.5 to 2 mils is preferred. As the dry film thickness increases, the bond strength usually increases and the rubber retention tends to vary. The highest rubber retention was observed with low Chemlok 702 and low dry film thickness. This high rubber retention can be misleading because, as I mentioned earlier, when there's a low pull force, there's less stress at the bond line, and this can allow for more rubber tear. It doesn't necessarily indicate higher overall performance. We have one final poll question. The question is, what is the end-use application for your castable urethane products? The data shows that pre-bake and dry film thickness are related. At a higher dry film thickness, we see more rubber retention without a pre-bake. At a lower DFT, we see more rubber retention with a pre-bake. In the hot tear testing, more rubber retention was observed without a pre-bake. And bond strength wasn't greatly influenced by a pre-bake throughout the study. Now, there are some key distinctions in the data based on the type of urethane compound. The A85, softer polyether-based urethane, is mainly unaffected by curative ratio and dry film thickness when there's no pre-bake. This elastomer also yielded the highest rubber retention under all test conditions. It makes sense that a softer stock resulted in the highest rubber retention because there was less stress at the bond line during testing. The overall highest bond strength was yielded by the A9-5 polyester-based urethane, and this was expected because the higher durometer compounds tend to yield higher bond strengths. This final chart lays out the performance based on the elastomers at each of the 3 dry film thickness conditions we tested. The elastomers are ranked from highest to lowest, from left to right in the chart, for both bond strength and for rubber retention. As you can see, the A9-5 compound almost always appears at the leftmost column for bond strength, and the A85 lies at the leftmost column for every pre-bake condition. Otherwise, we can see that there is some variation in the data across the elastomers tested. To summarize the presentation, Chemlok 701 performs on a variety of castable urethane grades. 701 performs in demanding high temperature and hot wet environments. The product is easy to use. The dry film thickness can be distinguished through the blue color contrast on a part, and 701 performs within a range of dry film thicknesses as the data suggests. Pre-bake isn't required for 701, and actually in most cases, higher rubber retention was observed without a pre-bake in this study. Lower 702 ratios are preferred unless the end-use environment is especially aggressive. And lastly, bond performance is dependent on the type of urethane and the durometer of the compound. We'd like to mention some acknowledgements. Special thanks goes out to Drew Botello for conducting the laboratory testing that generated the bond data that we used in this presentation. And also thank you to Jeff Means and Andy Ward for their contributions. If you'd like to reach out for more information, listed is my email and Brian's contact email. You can also reach out to us at our hotline at 1-877-ASK-LORD or visit the website link listed. Thanks for joining us today, and at this time we're going to open it up for any questions that you may have.